Hello everyone, myself Ashish Desai, Assistant Professor, Mechanical Department. Today we are going to discuss here unit number 3, Fluid Kinematics. So in previous lecture we have discussed regarding the fluid flow approach, that is Eulerian approach and Lagrange approach. So in that session we will discuss regarding the fluid flow and visualization of flow pattern. So first of all we look at the learning objective. So first learning objective is to know about method of fluid flow. Second learning objective is to understand about the visualization of flow pattern. So after this session, some learning outcome is there. So first learning outcome is the student will able to explain the method of fluid flow. So second learning outcome is the student will able to explain about visualization of flow pattern. So first of all, we look at the local acceleration and convective acceleration. So in local acceleration, it is defined as rate of change of velocity, or can say increase of velocity with respect to time. So that is called as local acceleration, that is by dou v by dou t. But in case of convective acceleration, it is defined as a rate of change of velocity with respect to change of position of fluid particles in a flow field. That means v dou v by dou s. Dou s means change with respect to space. So this is regarding the convective acceleration. And if you take addition of this local and convective, we'll get the value of total acceleration. So this is the regarding the acceleration. So here clearly mentioned that the convective acceleration. So already we discussed regarding this acceleration. So ax is equal to this formula, that is u dou u by dou x plus v dou u by dou y plus w dou u by dou z plus dou u by dou t. So this is a local acceleration. That means if you varies with respect to time, that can defined as a local acceleration. And if it is with respect to yes, that is space. Space means that coordinate system, that is x, y, z. So it is called as a convective acceleration. And if you take the addition of that, that is called as total acceleration. That is called as total acceleration. In that content, the local acceleration, so we have clearly mentioned in previous slide, dou v by dou t, and convective acceleration v dou v by dou s. So as clearly mentioned that total acceleration is nothing but local acceleration plus convective acceleration. Now we move for the example based on this local acceleration and convective acceleration. So the velocity, the problem is the velocity along center line of nozzle of a length L is given by V is equal to 2t in a bracket 1 minus x upon 2L bracket square. So where V is the velocity in a meter per second, t is a time in a second from commencement of flow, x, so here it is given that x is the distance from nozzle. So this is related with the nozzle, right? So calculate the local acceleration, convective acceleration, and addition of this, that is the total acceleration when t is equal to 6 seconds, x is equal to 1 meter, and L is equal to 1.6 meter. So this is regarding the problem. So first of all, we know that the relation for the velocity. So this is given in the figure, the problem. So we can take v is equal to 2t in bracket 1 minus x upon 2 L bracket square. This is given term. As we know that the local acceleration we can define by dou v by dou t, right? So we can take the differentiation with respect to t. So that becomes value. So when you define with respect to t, so this 2 is constant value, 1 minus x upon 2 bracket square is constant, and with respect to t, that means only remain 2 into this bracket, because we can take respect to t. That's why t is 1. Dou t by dou t is 1. That's why the local acceleration like that. Now we go for the putting the value of t is equal to 6 seconds, x is equal to 1 meter, and L is equal to 1.6. Okay, so put the value of this, t is equal to 6 seconds and L is equal to 1 meter, and sorry 1.6 meter, x is equal to 1 meter. So after this putting this value 1 as it is, x 1 meter, L is 1.6 bracket square. So after that we will get value of dou v by dou t. So this is called as local acceleration. Now we move for the value of convective acceleration. So as you know the relation between that, v dou by dou x. So here we are take respect to x because it is clearly mentioned that the x is distance from the inlet to nozzle. So that's why we can take the differentiation with respect to x. If it is given that y, we can write y. Okay, so that means difference is there. Otherwise we can take convective acceleration is v dou by dou x. Now we put the value of v as it is on that side, and we can take differentiate this to x. Okay, so like this. So this is v value. So instead of v, we can write 2t in bracket 1 minus x upon 12 bracket square into dou v by dou x. Dou v by dou x means what? We can differentiate this to this x. So 2t is constant. So x is in bracket. That's why the 2 is on. We can take it on that side. That's why 2 2t as it is. Correct. This v is, it is taken from v value. So this is v value, and now we can take this to x. That's why 2t as it is. 2 it is get in front of side. So that becomes x minus 2 upon L. So, but x is in bracket, that's why we can take differential with respect to x upon 2L. So that becomes only minus 1 upon 2L because it is constant. So with respect to x, that becomes 1. So this is the differentiation with respect to x. Now after simplification, that value becomes 4t square upon L into bracket 1 minus x upon 2L bracket is to cube, that is in sign of minus. Now we put the value of t and x and L. L is 1.6, t is 6, x is 1. So like this, same relation are here we can write. Now put the value of t, x and L. L is 1.6, L is 1.6, t is 6 second, 1 as it is, x is 1, 2, L is 1.6 and bracket is to cube. That value becomes minus 29.24 meter per second square. So this is the convective acceleration. As we know that total acceleration is nothing but convective plus local. So this is the relation. Now we take the addition of these two terms, that is local and convective. So already we calculate the local acceleration, that value is 0.945, and the value for the convective acceleration is minus 29.24. So that becomes total acceleration, that value is 28 minus 28.295 meter per second square. So this is total acceleration. Now we'll discuss regarding the types of fluid flow. This is next point. So there are different fluid flow is there. So first is the steady and unsteady flow. So this tells about the that factor of cross section. Then uniform and non-uniform flows. Then next term, that uniform and non-uniform flow is related with space. Then next term is laminar turbulent. So this saying about only the type of flow, that means in a flow is straight line or not. Then compressible and incompressible. So here especially we indicate with respect to density. So if it is known to the density, then we can easily know the flow is compressible or incompressible, rotational or irrotational. So if it is particle is rotated, that is called as rotational, and if it is not rotated, that is called as irrotational. So this is the terminology. Then one dimensional, two dimensional, three dimensional flows. So this is called as types of fluid flow. So again I repeat, for types of fluid flow: steady and unsteady, uniform and non-uniform, laminar, turbulent, compressible and incompressible, rotational and irrotational, and last one is one dimensional, two dimensional and three dimensional. So this is regarding the types of fluid flow. So first of all we will discuss regarding the steady flow. So here in that session we will discuss one by one. So first of all we will discuss regarding the steady flow. So as we know that the steady flow, in which the fluid characteristics like velocity, pressure, density it does not change with time. So it does not change with time, that called as steady flow. So we can take a mathematically. So velocity means we differentiate with respect to time in all direction, that is x, y, z direction. So if you take x direction, that is dou u by dou t. dou v by dou t, dou del by dou t. This is for y and this is for z. Again I repeat, this is for x, y and z. So you can take a 0. That type is called as steady flow. And if you take if you define for pressure, so dou p by dou t is equal to 0. Then for density, dou rho by dou t 0. So that time flow is steady. So the example is the flow through a conduit with a constant flow rate. So if you know that flow rate is constant, that time it is called as steady flow. So another example is the release the spillway notch with a constant head water. Constant head water means constant flow rate. So that time it is called as steady flow. So always remember that when the flow is in constant flow rate, that is called as steady flow. And in that case, the velocity, pressure, density does not changes. That characteristic is called as steady flow. So now next term, that is unsteady flow. So it is opposite of that steady flow. So unsteady flow is defined as the fluid characteristics, velocity, pressure and density. It changes with the speed time. That means mathematically we can write is not equal to 0, right? So for velocity purpose we can write in x direction dou u by dou t, for y direction dou u by dou t, then z direction dou w by dou t. We take not equal to 0. So this is regarding the velocity. And pressure, so it is not equal to 0. Dou p by dou t is not equal to 0. That is called as unsteady flow. Dou rho by dou t not equal to 0. So this is opposite of steady flow. So here the area will be vary. That means that pipe diameter is vary. So that time it is called as unsteady flow. So again I repeat, for steady flow and unsteady flow, when constant flow rate is there, we can identify it as a steady flow. And if it is varying flow, or you can say varying that cross section of pipe is there, then it is called as unsteady flow. So this is basic difference between steady flow and unsteady flow. Now we move for uniform flow. So uniform flow is nothing but the flow in which the velocity at time does not change with respect to space. So always remember that uniform flow and non-uniform flow while defining with respect to space. Okay. For steady flow and steady flow, we can define with respect to time. So for uniform flow, we define for space. Okay. So if you take equal to 0, that means it does not change. So this is the example of the longitudinal sections. So when the flow is in constant conduit, conduit means pipe with constant diameter. So constant diameter is there. Diameter is constant. That means there is no changes in the diameter size, right? So that time the flow is uniform. So always remember that it's the uniform flow is respect to space. Okay. So pipe is at a constant rate. That is called as constant rate means constant diameter. That is called as uniform flow. The non-uniform flow, it is opposite of that. That means the velocity at which the given time changes with respect to space. Okay, or you can say the flow in which the velocity at a given time changes with respect to space is called as non-uniform flow. So it is respect to space, right? So uniform flow or non-uniform flow we get defined with respect to space. So it is not equal to 0, then it can identify non-uniform flow. That means if there is changes in the diameter. So changes in diameter is what is called as non-uniform flow. The example is the variation of diameter of pipe, right? And you can say the non-prismatic. Non-prismatic means the changes in the pipe sections, that is bend or canal bend is there. That time the flow is non-uniform. Okay. So always remember that for steady flow and unsteady flow, we can define with respect to time. In case of uniform and non-uniform, we can define with respect to space. Is it clear? Now we move for the flow combinations. So first of all, we identify here the which flow is there. Is it unsteady, steady, or uniform, non-uniform? Okay. So first example is there, flow at constant rate. Constant rate means steady flow, and uniform cross section, that means uniform flow. So type is steady flow and uniform flow, right? Now we take next example. So here flow is a constant rate, but non-uniform is there. That's why we can take flow is constant rate means steady flow, and non-uniform flow is because non-uniform cross section there. That's why steady and non-uniform flow. Steady and non-uniform flow. So always remember that flow at rest constant rate means steady. Okay, and uniform cross section is there, uniform flow. Non-uniform cross section is non-uniform flow. Now next example. Flow is at varying rates. Varying rate means unsteady and is straight pipe. Straight means pipe means constant uniform rate. That's why we can say that unsteady and uniform. Okay, because uniform section is there. Now next example, flow at varying. Varying means unsteady, and here non-uniform means what? Unsteady, non-uniform. Unsteady, non-uniform flow. So this is the identification of flow combinations. So now next term, that is for laminar flow. So as we know that the laminar flow is nothing but the fluid particles moves along a well-defined path. That means each layer are straight and parallel. That is called as laminar flow. So this is diagram for laminar flow. The fluid particle is in a straight line, that is called as laminar flow, and which is parallel also. So here the capillary tube, or you can say flow of blood in veins, that is example of laminar flow. So here the three condition is there, that laminar flow, the flow moves slowly, viscosity is relatively high, then flow channel is relatively small. So therefore the fluid flow through capillary is laminar, and that satisfied three conditions. So there is no mixing between the layers, so it is parallel one, that is called as laminar flow. Now next flow, that is turbulent flow. So as you know that the particle, the flow in a zigzag way, that means it is not straight and not parallel, like this. The example is turbulent flow. So this is the diagram. There is no in a straight manner, there is in a changes in a zigzag flow. That means it is upper crust and lower crust, so that format is there. This is called as turbulent flow, which is not parallel, not straight. So example for that high velocity flow in a large gradient. So here is mixing with all the layers, that is called as turbulent flow. Okay, so this is not straighter and not parallel, that is called as turbulent flow. Now we identify laminar flow and turbulent flow, which is not in that format. Other format we can define for other way, that is that equation. That equation, that is Re means Reynolds number, rho is the density of fluid, V is the velocity, D is the diameter of pipe, mu is the dynamic viscosity, is equal to, otherwise we can say V is the velocity, D is diameter, and nu is the kinematic viscosity, because mu upon rho is called as nu. So that is the short form. So you can take nu, that is kinematic viscosity. So if you know this term, that is rho Vd mu or Vd mu, then you can calculate the value of Reynolds number. Okay, so this is the given information. So here it is clearly that mention, if it is less than 2000, the Reynolds number is less than 2000, then flow is called as laminar flow. And if it is the Reynolds number is less, that means that 4000, okay, that is called as flow is in a turbulent. So it is in between 2000 and 4000. Okay, so that is called as turbulent. And if it is less than 2000, you can say that it is a laminar flow, or you can say more than 2000, so is less than 2000, so it is between 2000 and 4000, you can say turbulent. And is in, sorry, this is called as turbulent flow or laminar flow, it is mixed flow. And if it is greater than 4000, it is greater than 4000, that is turbulent flow. So again I clear it there. Reynolds number is less than 2000, that is called as laminar. If it is Reynolds number is greater than turbulent, and if it is 2000 and 4000, it is in between there, that is called as transition flow, or you can say laminar or turbulent. So here laminar flow is like this, turbulent flow is like this. So for the purpose we observe these particles. but instead of that we can find out the Reynolds number, and then we directly will get the information about type of flow, that is laminar or turbulent. Okay, now next, that is one dimensional flow. So here the parameter flow is in velocity, is a function of time, and one space coordinate is there. That time is called as one dimensional flow, that is u is equal to fx, and about other velocities all are 0. That means v is equal to 0 and w is equal to 0. So that's why that velocity component becomes like this. Okay, an example is the flow of pipe, where average flow parameter is considered that flow analysis. That means only we are consider the length parameter. So that is the one dimensional flow. So this is longitudinal section for rectangular channel. Next, that is a two-dimensional flow. So in that case, that two-dimensional flow, their function is in two dimension. So here two rectangular spaces there. So here considering with x y coordinates x y. Okay, so there are two-dimensional form is there. So that is flow parallel plates, or you can say mean stream wide or river. So you can streaming or like this. So that can two-dimensional flow is there. And for three-dimensional form, we are defining in a three-dimensional that form, that is in the x y z directions. So all the direction is in a mutually perpendicular. So that is u is a function of x y z, v is a function of x y z, w is also a function of x y z. So this is nothing but three-dimensional flow. So here the flow converging channel, that is you can say nozzle. So that is nothing but three-dimensional form. So while defining the stilling basin or basin, that basin area is there. So when your storage dam, the dam water is there, so that is nothing but a basin over here in opposite of that side. So this is the change the width or depth and the length also. So this parameter will consider here, that is called as three-dimensional flow. Now we move for the next type of flow is rotational flow and irrotational flow. Rotational flow means the flow particles, or can say fluid particles, rotate in about their own axis. That is called as rotational flow. So example is motion of liquid in a rotating tank. So that is called as rotational flow. And for irrotational flow, the fluid particle does not rotate about their mass or centers. That is called as irrotational flow. An example is the basin, wash basin is there. So from the drain hole, the stationary tank is there. So that time the observed flow is irrotational. So here the clearly mentioned that this that particle is go from the drain hole, that is in straight way, that is not rotating. That is why it is called as irrotation flow. And here the fluid particle is rotational. So this is called as rotational and irrotational difference. Now we move for compressible and incompressible flow. So while defining the compressible flow, if it is density changes from point to point, that is called as compressible flow. So example is the gases. So flow is if it is considered in a orifices, nozzles and gas turbines, so that time the flow is a compressible. Incompressible flow, therefore in that case density is remain constant. That's why I can write a relation, that is rho constant. So in incompressible flow you can write rho constant, and compressible flow it is changes. That's why I can change not equal to constant. Okay, so here incompressible flow, that is subsonic and aerodynamics sections. We observe this. So here example, that is incompressible and compressible. Compressible flow means when you apply the pressure, the changes in the volume, but in incompressible flow, the volume does not change. So when you apply the pressures, so this is called as compressible and incompressible differences. So generally, incompressible flow is or fluid is the liquid, and compressible flow is or fluid is gases. Okay, so this is regarding the difference between compressible and incompressible flow. Now we move for the formula, or can say problem. So this is the relation it is given in that case. In a fluid, the velocity fluid is given by capital V, that is velocity vector is given to you 3x plus 2y in a bracket I plus 2z plus 3x square bracket j plus 2t minus 3zk. Determine the velocity components. So here we can consider for UVW. So here we determine velocity components as well as speed at a 1 point. Similarly for 002 and time is given also there 2 seconds. Okay, so this is for speed at time for second point. And classify the velocity field as a steady or unsteady. So here we identify the steady or unsteady, uniform or non-uniform, one-dimensional or three-dimensional. So first of all, we know that the velocity field, that component or can say resultant, is know that. Now we compare with our resultant velocity. That's why we can write for this value is u, this value is v, and this value is w. So that's why it becomes u is equal to 3x plus 2y, then v is equal to 2z plus 3x square, then w is equal to 2t minus 3z. So this is regarding the uvw, right? Now we put the value of the 111, that is x is equal to 1, y equal to 1, z is equal to 1. So after putting the uvw, we'll get the like this format, that u is equal to 3x plus 2y, v is equal to 2z plus 3x square, w is equal to 2t minus 3z. After putting the value of 1 x, y1, z1, then we get the value of u is 5 units, v is 5 units, and w is 2t minus 3 units. Now for computing the speed, that means capital V is unknown, so that's why v square is equal to u square plus v square plus w square. So first of all, we can take square of this all the terms. So u is 5 square, v is 5 square, w is equal to 2t minus 3 bracket square. So after getting the equation, that 40 square minus 12t plus 59. So this is equation after simplification. So we can take square root of this. After taking square root, we get the value of v at 1 square root of 40 square minus 12t plus 59. So this is regarding the v, capital V. Okay. Now for we can put for 002 and t is 2 seconds. So this is right. So here the equation, we know that u and v and w. Put the value for x0, y0, z0, sorry, z2 and t is equal to 2 seconds. So it is mentioned previously. So we can put the value for x, y, z and t. So after that we will get the uv and w value. Then you can put the value for that equation, v square plus u square plus u square plus w square. After putting this value from this above mentioned that fronts, then find out the v square, and then taking the square root, we will get the value of v, that is 4.472 units. Now as you know that the equation is given that capital V. So from that equation we have to find out the flow is uniform, non-uniform, that steady or unsteady. So here the first thing is there, if it is t is present in that equation, if it is any equation t is present, we can directly write as a unsteady flow. Is it clear? Then second point, for identification of non-uniform and uniform flow, here clearly mentioned that the flow is in changes in x direction, because the value of x and y and z, it changes. That's why that change in a space, that's why you can check the non-uniform flow. Okay, this is nothing but non-uniform flow. And here all term is present, x present, y present, z also present in that equation. That's why it is called as three-dimensional flow. So this is regarding the problem. Now we observe for visualization of flow pattern. So I'll define the visualization of flow pattern. So it is description of how fluid moves in a time and space. So it is useful for defining the properties of flow. So this helps to visualizing the fluid flow. So here the car is given, and we observe the streamlines as well as the pressure counters where it is maximum pressurized area is there, and another that object, that is cylindrical object, is there, and how the flow will be in tangent mode. and that flow changes, that momentum changes. So here observe over here, and you have to check the fluid properties over here. So in our next diagram, we observe the streamlines. For this is the wing, and here observe the flow pattern, and here the how flow around in a skilling athlete. So how we'll get the maximum pull-up sections, then you observe this flow pattern. So this is the advantageous method for visualizing this flow pattern. So actually the types of flow lines is there. So first is the streamline, second is the path line, and third is a stick line. So first of all, we look at the path line. So it is a stress made by a single particle over a period of time. So if you choose the particle and we can select for a particular time, so that tracing a path, that path is that tracing of that line is called as path line. Okay. So again, I repeat this term. When if you consider a single particle and in a particular time it traces a line, that line is called as path line. Okay. So the trace line is called as path line. Okay. Now the path line shows that the direction of particular particle as it moves, and in general the curve in a three-dimensional space, it is if the condition such that in a two-dimensional the curve becomes two-dimensional. So as per the dimensional form it can changes the forms. Now this is the path lines. So as you mentioned, if you consider the 3 points and you are tracing the line, that line is called as path line. Is it clear? Now we move for streamline. So streamline is nothing but imaginary line, or you can say imaginary flow, so that the tangents at a point that indicates the velocity. That means suppose the line is there, tracing line is there, and if you take a tangents, that is denoting the velocity, that is called as streamline. So whenever the tangent it can draws over there, that on imaginary lines within the flow, that called as a streamline. So here the cylindrical flow object is there, and here we can observe the streamlines. So in the equation of three-dimensional form, that is dx by u is equal to dv by v is equal to dz by w. So while tangenting format, so we can like write in that direction flow, and in a particular manner for steady flow, the path line and streamlines is identical, that means similar. And for unsteady flow, so it should be changeable, that means it is not identical. So this is the basic difference between steady flow and unsteady flow. So while identifying the steady flow and unsteady flow, we can define path line and streamline, so we can easily identify steady or unsteady. Okay, so this is the one methodology for finding out this method. Now we move for stream tube. So bonded type of the group of streamline, that is called as stream tube. So number of stream tube is there. So if you say the number of streamlines is there, and if you formulate as a tube, that is called a stream tube. So this is called a stream tube, and this is observed in a pipes and nozzles. So this the stream tube has a finite dimensions. There is no perpendicular to streamlines. There is no flow across the surface. So that is the formation of stream tube. The shape of stream tube changes from one instant to another because of change in the position of streamlines. Now we observe the stick lines. So the stick line is a curve or in that picture of location of fluid particles which have passed to a given point. So example for that is a smoking, or can say smoke coming from chimney. So here you can check out the fluid particles path, or can say locations, and if you traces this line, that is called as stick line. Okay. Similarly for in experimental format, the die injection from this point. So here color dye is there and it is injected in flowing fluid. So it is injected in flowing fluid. So if flowing fluid is in that channel and we are sending the dye into this point, and then the colored filament lines will be observed over here. So that observe the stick lines, so that fluid particles will be tracing the path in a particular locations that called as stick line. So this is regarding the stick line. Thank you. So this is about the flow visualization. In next lecture we will discuss regarding the continuity equation.